times 790 divided by 3 to two significant figures is 1,200 kilojoules of heat is required.
Which element in each of the following pairs has more non-metallic character? Non-metallic character usually relates to its ability to hold an electron tighter. A. Boron or aluminum? Boron is higher in the group, so it has more non-metallic character. B. Germanium or bromine? Germanium or bromine? Bromine has a higher group number, it's halogen, so it's more non-metallic than germanium. C. Indium or selenium? Indium and selenium. First, we look at the group number. Selenium has a higher group number, that's chalcogen. So selenium has a more non-metallic character than indium. D. Chlorine or tellurium? Chlorine has a higher group number, it's halogen, it's more non-metallic than tellurium. And besides, it's also up in the group, which also enforces this answer. So chlorine.
So a method of producing phosphine PH3 from elemental phosphorus, P4, involves heating P4 with water to produce PH3 and phosphoric acid. We're asked to balance this equation, and this one happens to be a pretty tricky one to balance, just the way that the elements are broken apart. And the one that I see is on the right-hand side, I see oxygen with 4, and then I see the oxygen with 1. So that means that in order to make the oxygen balance, and then of course we have the hydrogens, we're going to need multiples of 4. And since we have 3 hydrogen and 3 hydrogen, I think the best number to start with is going to be 12. So if we put 12 there, then the phosphorus is the last one we're going to balance. So if I put a 12, then that means that I need to come up with a way to get 24 hydrogen on the right-hand side. So let me put the 12 here, so that would be a 3 would make the 12 oxygen. And then that gives me 9 hydrogen on that side. So now I need to be able to come up with 24 hydrogen. Well, if I have 9, if I come up with 15, that's going to give me 24, and I need a multiple of 3. So I'm going to put a 5 there. And then that gives me now, I have 12 oxygen on this side. I have 12 oxygen on this side. For my hydrogen, I have 9 plus 15 is 24 hydrogen. And I have 24 hydrogen over here. So that looks pretty good. So now we're going to go to the phosphorus. So I have 3 phosphorus from the phosphoric acid and 5 phosphorus from the pH 3, which gives me 8. So that means we're going to put a 2 here. So that would be my balanced chemical equation. So I hope that you found that helpful. Have a great day.
Okay, so this will be a review of how to determine the hydrogen ion or proton concentration, this H plus here, in a solution at a given pH. So you can see the mathematical relationship that I have written here. Just a quick note on this. So I have it written as the concentration of H plus. Sometimes you'll see this equation written as the H3O plus, the hydronium ion. For the purposes of these types of calculations, they mean the same thing. So you notice that I have this written in brackets here. Just a quick reminder, whenever we use this brackets, we're talking about the concentration of these species in molar or moles per liter. So if we look at this equation, it's expressed in terms of the pH equals. So we want to essentially rearrange this equation so that we can get the concentration of the hydrogen ion by itself if we want to determine this value. So we can first divide each side of this equation by -1. This will get rid of that negative sign in front of the log value here. So if we have negative pH equals the log of the concentration of the hydrogen ions or the concentration of protons in solution. So we often just write this as the log of the value. We're talking about logarithm to the base 10. Usually if that's not explicitly written, that's implied. So we can do sort of an algebraic transformation in order to get this concentration value by itself. So if we take the base of the log, which is a base 10, and we raise it to the power on the left side of the solution, which is the negative pH, we can set this equal to the concentration of the hydrogen ions. So this is also sometimes referred to as taking the anti-log. So if we have the concentration of the hydrogen ions is equal to the base of the logarithm, which is 10, raised to the negative pH power. Okay, so now that we've rearranged the expression, we can basically just plug in a value for the pH, put it in the calculator, and then calculate the concentration of hydrogen ions in solution. So we can do a couple examples to show this. So let's start off with doing where the pH is equal to 8.34. So if we have a pH of 8.34, we can plug that in as the exponent in the solution or in the equation here. So if we want to know the hydrogen ion concentration, we know that we can solve this by doing 10 to the minus 8.34 power. It's just important to remember when you're doing these calculations that you always remember this negative sign in the exponent here. So if you were to put this in the calculator, go ahead and solve that. So it'll come out to 4.6 times 10 to the negative 9. So these values are pretty much always going to be expressed in scientific notation. So that way we're not writing this out to too many decimal points. So we want to make sure that when we're solving these types of equations that we're using the appropriate number of significant digits. So when you're taking the anti-log of a number, you want to look at the exponent here and see how many decimal places we have. So in this case, we have 8.34. So we have two numbers after the decimal point here. So these numbers after the decimal point are going to determine the number of significant digits in our answer. So we have two numbers after the decimal point here. So we have two significant digits in the answer. So if we do another example, let's say the pH is 5.90. And because we're trying to use the correct number of sig figs, we want to make sure that we are writing out the 0 at the end. So not leaving it at 5.9. So we have 5.90. And we can do this in exactly the same way. So we have the concentration, hydrogen ion is going to equal 10 to the negative 5.90. And then you can go ahead and put that in the calculator. And then you should get 1.3. Again, we're doing the correct significant digits. We have two decimal places here, so we want two sig figs in our answer. We're expressing it in scientific notation. So we have 10 to the negative 6. And just as a little reminder, again, we should always be using units. So when we're talking about something in the brackets like that, this is in molar. So we have the capital M. Okay, so let's do one more. If our pH is equal to, let's say 2.65. So you can go ahead and plug that into the equation. So we're going to have 10 to the minus 2.65. If we're considering the sig figs, same thing, two digits after the decimal point. We want two digits in our answer. And then this should come out to 2.2 times 10 to the negative 3. And then make sure that you're remembering your units. So we'll do capital M for molar. Okay, so we'll do one last example. Let's say that our pH is 12.6. So you'll be plugging this into the equation the exact same way. So have 10 to the negative 12.6. We just want to make sure that when we're determining the sig figs for the answer, that we note that the number of decimal places here is not the same as the previous examples. So we now only have one digit after the decimal point. So we will be using one digit in our answer. So this is going to come out actually to 3 times the negative 13. And then this is molar. So we can also do a quick check of our answer to make sure that everything makes sense here. So we know that acidic solution should have higher concentrations of the hydrogen ion in them. So if we're starting at the lower end of the pH scale, we know it's more acidic. We see that we do have greater concentration. We can tell this by the lower exponent on here. And then as we start to get up to higher pH, this number is getting smaller and smaller, so there's less and less of the hydrogen ions in solution. So we have the greatest concentration for this pH of 2.65, and then as we start to move up the pH scale, you can see with these exponents here, the number's getting smaller and smaller because we have more and more decimal places out to the left here. And then once we get
Henry's law constant for hydrogen in water at 25 degrees centigrade is 7.7 times 10 to the power negative 6 molar per kilo Pascal. And for nitrogen in water at 25 degrees centigrade is 1.4 times 10 to the power negative 5 molar per kilopascal. Each gas present at 253 kilopascal pressure. We have to find out the solubility of each gas. Now, Henry's law expresses the relationship between the pressure and the gas solubility. S is G, the solubility of the gas is K, this is Henry's law constant, times Pg, partial pressure of the gas over the solution. Now for H2, Sg is the constant, which is 7.7 times 10 to the power negative 6 molar per kilopascal times the partial pressure 253 kilopascal. And the value for this one is 2.0 Sg, 2.0 times 10 to the power negative 3 molar. Okay, now for nitrogen, Sg is constant here is 1.4 times 10 to the power negative 5 molar per kilopascal times 253 kilopascal. And the Sg for nitrogen is 3.5 times 10 to the power negative 3 molar.
In this video, we want to use Henry's law to determine the concentration of oxygen in water at 25 degrees Celsius under 1 atmosphere of air pressure. So Henry's law says that the concentration is equal to Henry's law constant times the pressure of the gas. So in our case, the concentration of oxygen will be the Henry's law constant, which is given as 1.3 times 10 to the negative third mole per liter times atmosphere, multiplied by the atmospheric pressure of oxygen. So if the air pressure overall is 1 atmosphere, and the air is about 21% oxygen, the pressure of oxygen by Dalton's law of partial pressures will be 21% of 1 is 0.21. So we can plug in 0.21 ATM. ATM on the top and bottom cancel out, and we're just left with moles per liter, which is the unit that we would want. And then we have the value is going to be 2.7 times 10 to the negative fourth, the right number of significant figures, moles per liter, or molar. And then the second part of the question is more conceptual. Can we survive without hemoglobin, which hemoglobin transports oxygen throughout our blood? So the volume of human blood is 5 liters. So if we consider this is the concentration of the oxygen in our bloodstream, if we multiply by the total volume of our blood, we'll get the amount of oxygen that's available in our blood, which is 1.4 times 10 to the negative third moles. So it's a very, very, very small amount of oxygen, and it would be difficult for it to diffuse throughout the body on its own and get to the cells in a quick enough manner for the cell's active processes. That's why hemoglobin is present, to sort of facilitate that transportation. If we had a lot more oxygen available, it would flow more easily. But given the small amount, hemoglobin ensures it gets where it needs to go and that our body can maintain its proper function, because the cells need oxygen for their processes like respiration to produce energy for our bodies. Hope this helps.
So we're going to collect a sample of gas over